Okay, so we'll start by discussing what is a graph, right? So a graph is a set of vertices and edges. An edge is defined as like a pair of two vertices, v1, v2. Uh, in an undirected graph, this is an unordered pair, undirected graph. Okay, so your vertices are going to look like v1, v2, v3, and this edge is going to look like v2 comma v3. So note that which is equal to v3 comma v2. Oops. So that's what a graph looks like. Okay, so it's just a set of vertices, set of edges. Edges are defined as pairs. Okay, and what we can do now is that what do you say? Now, if I give let's not talk about and the number of vertices is called as the order of the graph. Order of graph and number of edges. So is called as size of graph. These are just definitions, but you're going to very often see consider a graph with order A or something, in which case it's important to know that's just saying that there are A vertices in the graph. Um, Now, that's a graph. Now, very often in Olympiad, you're going to see the term simple graph. So, do you guys, can any of you guess what like would make a graph simple?
At most one edge joining two vertices.
So, so condition one is at most one edge between two vertices. Two vertices. And other condition is that there is no self loops. Okay. So, second condition is that E belongs to E uh, that doesn't exist. E belongs to E such that vi comma vi equals E. Okay.
Can I explain this once?
What this basically means is that there is no edge which connects the same vertex to itself. This is called as a self loop, and in a simple graph, we assume that that do not exist any self loops.
Uh, so, like, if I wanted to give an example, suppose we have a rectangle type of graph, then yeah. So if you name this rectangle A B C D, is this a simple graph?
Yeah, this is a simple graph
But
because
B and
all
D,
edges. Oh,
but B and D and A and C are not connected.
yeah, so it's at most. So you can have 0 or 1. Okay. So what this specifies is that you can't have A B like two times. This is not a simple graph. But you don't need every edge to exist. If every edge exists, we call it a clique or a complete graph. Okay. A simple graph. So this this is considered a simple graph because we have that between any 2 points there's at most one edge. So between A and C, for example, there's 0, which is less than. So by at most, I mean less than equal to one edge. Right. So this means that 0 is valid and 1 is valid, but you can't have two or three edges between A and B. Does that make sense?
Yeah.
And you told if A and C and B and D are connected, then it's a complete graph.
Yeah. So we call this a complete graph or a clean
Oh, thank you.
graph or like so four clean. So this is denoted by K4. we don't ask where the K comes from. I'm not very certain either, but it's called K4. Okay. So now we're just going to have to have a couple more definitions. So we call two vertices adjacent. So V2 adjacent to V3 if and only if V2 comma V3 belongs to H set of vertices which will denote with capital V and edges which will denote with capital E, by the way. And this is if, so basically if there's an edge joining V2 and V3, V2 is adjacent to V3. Okay. And here we're dealing with undirected graphs. So like V2 V2 being adjacent to V3 means V3 being adjacent to V2. Okay. Does this make sense? What two vertices
Yeah.
being adjacent means? Cool. Now we have also degree of vertex. Okay. So the degree of vertex is number of edges from degree of V is equal to number of edges from V. So degree of V3 here is 1 because there's one edge with an endpoint at V3. Degree of V2 is similarly 1 and degree of V1 is 0. Does this also make sense?
Can you repeat this?
What? Oh yeah, sure. So I think I should probably not do it here. Let's go back to rectangle graph, right? So degree of a vertex is equal to number of edges. So degree of V is number of edges that are that have one endpoint in, have one point at V. Okay, so this is what degree of vertex V is. So for example, degree of A here is 2 because there's 1, 2. These two
Right.
edges have one endpoint at A. It's not 3 because CD and BC don't have an endpoint at A. They have endpoints as C and D, B and C respectively. Similarly, degree of A, B, C, or D here is 2. Okay,
Yeah.
does this make sense? Good. Now we have these three things: path, cycle, and walk. Okay, so these are just going to be terms that you're going to see pretty frequently if you try solving graph theory questions. So that's why I'm just going through that. Ask like if you have any doubts whatsoever in like any of the terms. So now what is a path? So I start. So if I have a graph like this, V1, V2, V3, V4. So V1, V2, V3 is the path. Path. Okay. A path is string VA1, VA2, dot, 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 VAK, uh, such that VAI, VAI plus 1
Or adjacent.
are adjacent. Exactly. Okay. Okay. This is condition 1. Okay. And condition 2 is AI not equal to AJ for all I not equal to J. Okay. This means that all the edges, all the vertices are unique. So, for example, if I had V5, V6, V4, and then V7 again. So V4 again and then V7. Right now, V1 to V7 is no longer a path because we have V4 gets repeated in between. Okay, so in a path, you don't visit the same location again.
Can you explain this one again?
Yeah. So the point in a path is that wait, yeah, in a path you don't visit the same vertex again. Yeah. So all vertices that belong to a path are unique. Okay, so when I have the path v1, v2, v3, v4, that's fine. Oops, v1, v2, v3, v4, that's fine because all of the vertices are distinct. Okay, but when I go to v5, v6, v4, and then v7, right? So v1, v2, v3, v4,
We have visited
v5,
V4 twice.
yeah, v7. So this is not a path. Okay, because v4 is there once and v4 is there second time, so that contradicts second statement because a4 will be equal to a what is it, 5 6 7. So yeah, a7 is equal to a4 but 4 is not equal to 7, right? So this contradicts condition 2. Okay, but it does satisfy condition 1, so it's a path if and only if both the conditions are satisfied. Similarly, v1 v3 is not a path because v1 and v3 don't have an edge connecting them. Does a path make sense?
Yeah.
Okay. Now, what I want is I want a cycle. So when do I have a cycle? Cycle is like a path. So cycle is like a path. And then after the last vertex, I want the last vertex and the first vertex have to be adjacent. So it's a path with this additional condition that VAK comma V1 are adjacent.
Yeah.
Yes. Okay. So here the path will be V1, a path will be V1, V2, V3, V4. But V1, V2, V3, V4 won't be a cycle because V1 and V4 are not adjacent. But V1, V2, V3, V4, V7 will be a cycle as well as a path. Make sense?
Have to write the
Yeah.
name of the last vertex in the path, in the cycle, sorry.
You write V7 in the cycle. You don't repeat V1. So I mean, that's really a nomenclature thing. Like if you see in a question that someone says a cycle V1, V2, V3, V4, V7, V1, right? That question is not going bonus. Like it's clear what they mean. But
Yes.
and similarly, if you write that in a contest, I highly doubt that any of the graders are going to cut marks. Okay, so for all practical purposes, it's just a matter of nomenclature. As long as what you say is clear, it's fine. But very formally speaking, the best way to write a cycle will be oops, will be V1, V2, V3, V4, V7 is a cycle.
Oh, thanks.
Okay. But you may see, consider cycle V1, V2, V3, V4, V7, V1. Like you may see this in like when you're solving a question or you're checking someone's answer on like AOPS or something, you might see some stuff like this written. But this is like the best way. So this is the best way. Does this make sense? So generally, you wouldn't want to write the initial vertex again, but some people do. It's just a matter of nomenclature. But
So
however you want to
V1,
write it.
V1, V2, V3, V4, V5, V6, V7 is not a cycle because some parts are open.
V1, V2, V3, V4, V5, V6, V4, V7 is not a cycle because you repeat V4.
Right.
And I was
But you can,
curious, is V4, V5, V6 a cycle?
yes, that's a cycle. So
Okay.
V4, V5, V6 is a cycle. Also, another thing that can be of contention, would you all consider V4, V5 a cycle?
No.
Yes, it's generally not considered a cycle, but by this definition, it's fine. So we
Yeah.
add the additional condition that length of string
Greater
is
than.
greater than equal to 3. Okay. This is when like simple graph case. This is for simple graph. And like the point is that we would consider if we had v4 v5 and it's no longer a simple graph, right? Then if I had this, we would consider v4 v5 a cycle. Okay, but for our current purposes, we're going to assume all graphs are simple enough.
Okay.
Okay, so this is a cycle, is a cycle, not a cycle, not cycle. So this condition when it's a simple graph, and this is the condition when it's, what do you say, not a simple. Like this sort of stuff happens when it's not a simple graph. So we're not going to go into that. Uh, and the last thing that we had, walk, right? So a walk allows you to repeat vertices. All that's not allowed to be repeated is edges can't be repeated. Edges can't be repeated. Okay. So what this means, for example, is that, so for example, this is now a walk. Okay, because if you go edge to edge, you are no longer repeating any edges because every edge you use is distinct. However, you repeat a vertex, but that's fine when it's a path. Sorry, when it's a walk, but it's not fine when it's a path. Does this make sense?
Yeah. So what is a formal definition of a walk? No
So a
edges
formal
repeated.
definition, yeah. So what this means is that uh, ai ai plus one not equal to ai plus aj aj plus one. So because you're viewing all of these as strings, right? So you're going
Yeah.
to have the adjacency condition. So you'll have, this is condition one. So this will be condition one. Condition two will be a is not, so the substring ai plus one is not equal to substring aj plus one for all I comma I not equal to j.
I
In a
think
walk,
condition
do
one
we
and
have
two
a
must
cycle?
be the same thing, right?
What?
Like, I think condition one, like, which one is condition one here?
So this is condition one. So VAI and VAI plus one. Oops. Yeah. VAI, comma AI plus one are adjacent as condition one.
Okay. Okay, got it.
Okay, because we only care about like when they're adjacent, right? So I don't want
Yeah,
my
right.
walk to suddenly be V1, V3. That's
Yeah.
bad. That's we don't like that. But
Yeah.
In a
now I
walk, do
want
we have a
edges.
cycle?
In a walk, can you have a cycle? A cycle is considered a walk generally. I don't think like you're gonna specify. As far as I know, I do consider cycles as walks, but like, yeah, cycles are walks. I'd say.
Like, is V1, V2, V3 a walk then?
Is V1, V2, V3 a walk? Yeah, V1, V2, V3 is a walk.
And
Y-
is like V1, V2, V3, V4, V7 a walk again?
Yeah, that's also a walk.
Okay.
Every path is going to be a walk. I think
Okay.
you can try and show that, but like as long as vertices are unique, you're definitely going to have that VI is not VAJ. Like AI can't be AJ. Then AI plus one can't obviously be AJ plus one, because if that were
Okay,
the
I,
case,
I
then
think,
AI is AJ.
like, what is the difference then between a path and a walk?
So V1, V2, V3, V4, V5, V6, V4, V7. Is that a path? The this thing.
No. No.
But is it a walk?
Yeah,
Because
it
for
is. Okay.
every time
Yeah.
that to like, you don't have the same edge being traversed twice is how you
Yeah.
can visually view it. Otherwise you can think about it like, for example, you have v3 v4 and v4 v5, but you also v4 v7. So v4 is repeated, but never do your v1 v2 gets repeated anywhere. Never do your v4
Yeah.
v5 gets repeated anywhere, right?
Right.
So you have that none of the edges get repeated.
Okay.
Note that all of these are defined on like a simple graph. uh, so, for example, you can have some edge repetitions when it's like, what do you say, like not no longer a simple graph. But for practical purposes, we're dealing with simple graph right now. We're not dealing with not simple graphs, because if any of you have like done questions that involve like graphs which are not simple, then you might sometimes see walks which break this condition, or like path is going to be the same. Cycles like this one. So don't, yeah, this is only when the graph is simple. Okay. Otherwise, it's like number of occurrences of AI plus 1, comma AI plus 1, comma AI I is less than equal to num number number of times, number of edges between AI, VAI and VAI plus 1. So this is like for a no longer simple graph. But like in the case of a simple graph, this is like 1, because we have AI and AI plus 1 are adjacent. So that will like force number of edges to be less than equal to 1. Okay? Does this make sense for like a not so simple graph?
Yeah.
Okay,
So
cool. Yeah, you're saying?
just a second. This makes sense. No. What do you mean? Like no occurrences of the.
Number of this is like number of.
Okay, so the number of occurrences of AI and AI plus one, comma AI plus one and AI is less than equal to one.
So like either 4 comma 5, oops, 4 5, or 5 4, right? So number of times that this and this occur is less than equal to. So for example, if I had, like, let's just say 3 edges and I had 4 5 4 5, right? So this is a walk because number of
Right,
occurrences of 4 5 and is total 3.
makes sense. Makes sense.
But this is, if I add a 4, no longer a walk. No longer walk. Okay, this is because then the number of occurrences moves up to 4. Okay, and that's too much because there's only 3 edges. Visually, if you want to think about it, you go through here. So you go from 4 to 5 the first time, then you go 5 to 4, and then you go 4 to 5, and that's 3. But now, if I want to go back from 5 to 4 again, I literally have no edges left.
If you have a
Make sense?
problem when you have to count the number of walks or paths, wouldn't it be very difficult to do so? Because there can be numerous walks when we hit the image twice or thrice.
You want to count number of walks in a arbitrary graph.
Also, are these like, is it okay to use this without definition because these are too many
Yeah,
difficult?
yeah, these are like completely fine to use without definition. The point is that it's so fine to use without definitions that the questions are going to give them to you without definitions. Okay, they'll be like, consider an arbitrary walk, blah 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 blah, and then you'll be like, what is a walk? What is a path? And like for me, for example, I keep mixing up path and walk. Okay, so like just be careful. So like try and remember them. Like I'm like the reason I'm going into definitions is because sometimes these will be stated to you without definitions and you'll have to understand what they mean. Does that make sense? Like you're completely fine to use these in like your answer without definitions.
I'm a little worried these without the questions are framed without these in definition.
Yeah, that's fine. Like they might say consider, so question might be consider a path, a path p1 pn or something like this. So like and perform the following.
Okay, one thing I wanted to ask, in a walk, edges can't be repeated, but vertices can be. But in a path,
Yes.
vertices can't be repeated, but edges can be.
Okay, hot minute. Can you repeat an edge without repeating any vertex?
No, yeah, makes sense.
Okay, so which is why we don't really have to go there. The point is that if you're repeating an edge, right, you've gone through here and you're going through this edge again. You've visited this vertex twice. You've visited this vertex twice. Okay, so if you're going to repeat an edge, you automatically repeat the vertices. Okay, so this actually
Yeah.
has the corollary that every
For every kind of
uh,
graph or just simple graph?
simple graph. Wait, no, no. Every kind of graph, if you repeat an edge, you're repeating the vertices. Every graph, not just every.
So every path is a walk, but every walk is not.
Yeah, so every path is a walk, but not vice versa. Is my handwriting legible? I mean,
Yeah, it's
A
fine.
little.
fine. I'll just.
It's too much fun.
Little.
Yeah, you guys can like understand when I speak. It's completely fine. I have to like work on my handwriting, and like it doesn't have that. It's like writing with like the computer. Oops. So that's paths, cycles, and walks. Are you guys clear with these three?
Yeah.
Cool. We're going to move to the next thing, which is connected graphs and disconnected graphs. So what do I mean by there's a connected graph? So a graph,
The question you gave, can I write the answer in your chat?
what?
The question you
Uh,
gave at the starting. I have
wait, what was the question? That was, it's
29.
most definitely not that. Like that's too large. It's like asked like for which values, by the way. So like specify the values or like give a characterization of all values, not just the number of, and your number of is also wrong. Pretty confidence.
Also, I wanted to ask one thing that if you just take it in a subset order, then is path the biggest set, then comes cycle, then comes walk, then comes cycle.
Every path is a walk. So if you're going to start off, every walk has to be a.
No, no. What I'm telling is that every path is a walk, and every walk is also a cycle. What I'm saying
Every
is it?
cycle is a path. Okay,
Yeah,
exactly.
every
So
cycle
what
is a
you'll
path.
have, you'll have that cycles are a subset of path,
Yeah.
are a subset of walks.
Wait, wait. Just a second. Every path is a walk. Ah, right.
So it'll look
Okay.
like this.
So yeah, makes sense. The walks are the biggest.
Uh, where like cycle is defined without repeating the final vertex, by the way.
Makes sense.
So, for example, V1, V2, V3, V4, V7, V1 is not a subset of path, but like we write it in this format, it's a subset of path, which is also why this format is better, guys. Like, just use it. Okay. Yeah. Anyways, I was talking about connected graphs. Let's talk about when is a graph connected. When connected, right? So consider Vi, comma Vj if all for all Vi Vj if a path Vi Va1 A1 Va2
Till
dot
VJ
V.
exists.
Yeah. So it should start at I, end at J, and can have as many elements as you like. Exists implies connected. Okay.
Shouldn't I be equal to J to be for it to be connected?
No. What do you mean I equals J? Like,
Kind of like self-linking idea, right? If I equals J.
So then you'll have a cycle. For example, we consider the
Yeah, it's
following
not a
graph.
simple graph anymore, is it?
It's not necessarily a simple graph. The same definition works for even if it's a
No,
complex
no,
graph
no,
because path doesn't really change so much in a
no, no. I'm
simple
asking
form.
that isn't connected imply cycles?
No, for example, a tree is a connected graph. So V1, V2, V3 is a connected graph. The point of connected graph, if you want to think about it visually, is that I'm connected to every other point that is in the graph. So wherever I am, I can walk to every other point in the graph.
Ah, okay, makes sense.
Okay.
Graph with one
So
vertex is a silly graph, I think.
what?
What information can it give?
Can you repeat what you said?
Graph with one vertex is a silly graph. Like, what information can it give?
What do you mean a semi-graph? Uh,
No, say
probably
silly graph. Uh,
say.
that
Oh, it's generally so. If mod v is oops, mod v equals 1, we usually call it the trivial graph. Trivial graph. I think so. What can you? Your question is what can you say about it?
what information will you get?
I mean, it really depends. What can you say as what information? So you can have this is equal to 1. Assuming that's a simple graph, you'll have mod e equals 0. Uh, then you'll also have that it's what else do you want? It'll be connected because there's literally only one vertex. Uh, there is the there's the trivial path. That'll be there's no walk because a walk requires at least 2 points. There's no cycle. So that's oh well walk and path. Walk and path. That's all you can really say about a trivial graph. Like there's not a lot to do with the trivial graph, right? So that's all you have. Also, like you can say stuff directly without raising your hands. Probably. Like if you have any doubt, there's no need to like raise your hand. Okay. Um, does that clarify what information you can say about like the trivial graph or like the one vertex graph?
Yes.
Okay.
I had a question about connected graphs.
Yeah.
Like if in the diagram you've drawn, that is the like V1, V2, V3. If we join V1 and V3, does that still remain a connected graph? Like,
Yeah. So yeah. So
not
for
that
any
one, not that one, the small one. Just under where you wrote connected graph.
oh wait, I see. Yeah, yeah. Oops, this one. Yeah, it
Yeah.
remains connected.
Okay,
Uh,
and if I have like four vertices, can you draw this, please?
yeah. Sure. I think I'll. Yeah. Uh, yeah. So I have 4 vertices.
And if I draw all the sides and both the diagonals, that is a connected graph. So is there any other way to draw a connected graph using four vertices?
So you have just the sides is a connected graph.
Okay, but I can't go from all the vertices to all the vertices, right? I can't go from V2 to V4 or V1 to V3.
So V2 I go to V3, and then from V3 I go to V4. So this is a
Okay.
so V2 V3 V4 is a path.
Okay, right. But like,
And
uh, yeah, okay. But I can't go from V2 to V4, right? So that's not a problem in a connected graph, is it?
so there needs to be a path. So it doesn't mean that V2 and V4 are adjacent. It means that there's a path from V2 to V4. So is this a path?
Yes.
Okay. So then this means that V2 is connected to V4 and vice versa in like a undirected graph. So you
Okay.
can just imagine this as like imagine the vertices is like tiny little cities, and like
Okay.
edges is roads. So can I travel from V2 to V4? Like I want to go for an event that's happening at V4,
Yes,
and
I
I'm at
can.
V2. So I like travel to V3 first, and then from there I travel to
Yeah.
V4,
Yeah.
right? So that's all it means when I say that a graph is connected.
Okay, got
But
it.
whereas like if I had a V5 here that was not connected to V1 or any of these, from V2 I can't travel to V5. Like no matter what I do, I will never end up at V5.
Right.
So
But if
that's
I
when we say
join
that
V4 and V5, that's a connected graph, right?
then it's connected. Then it's connected.
Okay. But I still can't go from V5 to V1 in any way.
V5, V5, V4, V1.
Oh, actually, I can. Okay, got it.
Yeah. So actually, fun problem. I don't. Yeah. Yes, we should.
By the way, for this, like, can you go to that small graph once?
Small graph, as in the three graph.
Yeah, yeah.
I should have erased it. V1, V3.
Here, here you connected V1, V2, and two arrows. So if I just, yeah, can I draw the arrows? Like, we are just making a directed graph here. So if I draw
Okay.
from V1 to V3, is that connected?
Draw from V1 through V3. No, not by the definition of I stand at V1 and I walk to V3. So it's not, we don't consider this a connected graph because from V3 I can't go to V1 because from V3 there's like no way out. Like I can't even go anywhere from V3.
Right. So in this, it's not a connected graph. But if the arrow from V1 to V3 is reversed, then it's a connected graph.
Yeah, then it's a connected graph because from every vertex you can travel to any other vertex.
Works. It's okay.
Yeah. So are you guys clear what a connected graph is and what a disconnected graph is? A graph is disconnected if it's not connected. Like I don't think this. Yeah, I think I didn't mention that. But like a graph is disconnected if it's not connected. Yeah. Does this make sense?
Yeah, it does.
Then what did I want? I wanted distance between two vertices. So now I have. Let's take a rectangle graph. Let's take a rectangle graph. This rectangle graphs are nice. V1, V2, V3, V4. Okay. So now I define the distance to be, so distance is equal to shortest. Oops, wait, I haven't defined the length of a path. Uh, let's go here. So length of path, length of a path equal to length of string. So V1, V2, V3 is a three length path. Okay. V1, V2, V3, V4, V7 is a five length path. It's also considered a five length cycle. Okay. And a length of a walk is equal to length of string minus one. String minus one. Okay. So this is number of edges. This is mainly because path is vertex centered and walk is edge centered, like edge focus. So when we're talking about walks, we really care about the edges themselves. When we're talking about path, we're like more focused about the vertices.
Okay.
So a length of walk is number of edges in the walk, and like a length of path is number of vertices in the path. Length of a cycle is number of vertices, which is equal to number of edges in the cycle. Okay. So when you define a cycle this way, it's just number of vertices. Does the length of a walk, length of a path make sense?
Yeah, it does.
Okay, cool. So distance from V1, Vi to Vj is equal to length of the smallest walk. Smallest walk. Okay. So, for example, distance between V1 and V3 is 2. Okay. Distance from V1 to V2 is 1. This is because there's like a one length walk connecting V1 and V2, which is just V1, V2. And from V1 to V3, there's no one length walk, because if there was a one length walk, that would be V1, V3. But that is not a walk since V1 and V3 are adjacent. And uh, V1, V3, there's a two length walk, which is V1, V2, V3. Okay, so this is distance. If you have two disconnected points, we say that distance is defined. V by J is defined disconnected. Right. Yeah. So we like say that uh, it's, we say that's not defined. Like if we have to find out distance between V1 and V2 and there's no path. Uh, but if like the whole graph is disconnected, but V1 V2 has an edge, then distance is one. Distance V1 V2 equals one. Does this make sense?
Yeah.
Good. What else do I have? I have color. Good. So let's talk about graph coloring. So what would you guys like to color? Edges or vertices?
What is this
Uh,
meaning?
Both.
feel free to like play around. So the answer is we color both. So you have vertex colorings, vertex colorings, and edge colorings. Okay, and both of these are very different things that get talked about a lot. And like edge colorings has this whole section known as Ramsey theory, which is amazing. But we won't be covering that today. Today, our focus will be more on vertex coloring. Okay, so what do we mean by vertex coloring? Okay. So what I do is here I have a graph. V1,
Colored points.
V2, V3, V4. Does this seem like a nice graph to you guys, or do you guys want to like mess it up? Sure. Let's get this as the graph. Should probably be able to change the color. Yeah, I can change the color. Okay, so I can like color the points. Oops, I don't color them like that. No, let me change the color. Okay, never mind.
There is no edge connected to
Yeah.
vertices.
So the condition, oops, the condition is that no two vertices of same color are adjacent. Okay, so this is the condition. Okay.
Can you repeat from what is coloring, please, in brief?
What do you know? What is coloring in brief? Okay, yeah. Sure. So coloring is mainly we want to assign a certain color to every single vertex or edge. So what we're going to be specifically dealing here is vertex coloring for today's class. Yeah. So what I do here is I give every vertex a color. Okay. But now I want to sort of build stuff out of this. So like randomly coloring isn't going to give me a lot of information.
Like
So
I
what I
have a
do is,
question.
yeah.
What is the significance of coloring the vertices? I mean, like, how can that help?
So for example, we'll go to the uh, the problem. So this year, okay, wait. Can you clarify by what do you mean? How does that help? Do you want like a practical use case, or do you want to see problems where that's used?
Actually, I'm pretty new to graphs. I don't know anything about these. So, like, how do we use this practically in
Okay, how do we
problems?
use this pra- practically? Okay, so if you want to see how to use them in problems, I think like for example, one of the common things is that you're going to see vertex coloring as like themes of a problem. So this has a lot of flavor text into the problem, but like what this is saying is that you have a lot of cities. So this is a graph where your cities are vertices. I'm not going to solve the problem because that's it's a bonus well. I don't want to spoil that for people. You have bunch of different, and what you're told is that I can color. Okay, so you don't see the term color written specifically. What you're told here is that I can give each vertex a specific color such that uh, no two edges of the same color, such that no two edges of the same color are adjacent. So the favorite number of any, oops, I should probably use a different color that you can see. Yeah, so here colors are like favorite numbers. So, for example, uh, this is how it's usually stated in the problem. So, very often you might even see problems that directly just use vertex coloring. For example, this one, right? So, that's how it's used in a problem. You'll be given a problem where you're told like there exists a vertex coloring for such a graph,
Okay.
and you're asked to show some specific property about a vertex coloring.
Got it.
This is what we think. That's how it's used in problems. Practical use cases, as in like real life, you might see it sometimes when you're dealing with like. I will think about a practical use case sometime, like the real life where you might use vertex coloring in like graphs,
Okay.
but not props or PhD. Yes, that is the definition of like a vertex coloring. Okay, so it satisfies this condition. Okay, and we say a graph is k colorable if and only if yeah, if and only if we can color the graph with k colors, k distinct colors. Okay, so for example, this graph here is two colorable. But the moment I add this edge, right, there's no way to color the graph with just two colors.
Yeah,
So you're
three
going to have to
colors.
use it. So now you're going to have to three color the graph.
Yeah.
Okay, and now if I add this edge, then it's no longer even three colorable. You have to add in like four colors
Yeah.
because of four color. Make sense?
Yeah.
Good. Um, yeah. That's for coloring of a graph. Is everyone clear so far? This is the entire section of definitions. These are all the stuff that you're going to see. And these are things that you should hopefully be familiar with once you've done enough problems. Okay. Are you guys clear? Is there any doubts?
Yeah, it's clear.
Let me just go to chat because I've not opened it in a while. Is tree a connected graph? Tree is a connected graph. Uh, yeah, okay, someone's already clarified that. Yeah, a minimally connected graph is a graph. I'm not going to go into that definition. We do have a section on trees, like if we do end up having enough time. But if we go there, I'll define what a minimally connected graph and all is. Okay, so we're going to start with like problems. How long do you guys want? Like it's 4 problems, all of them should be. Oh, wait, complement of graph. Wait, one last definition. Complement. Oops. One last definition. Complement of a graph. Graph. So say that I have a graph like this. So I just have these two edges. So I say complement of the graph is I take all the vertices v and I preserve all the vertices v. And if an edge exists, I remove it. And if an edge does not exist, I add it. Complement. Does this make sense?
Yeah.
Okay. Are you
If
guys
it is
clear?
a colored graph, do we switch the colors or do the colors remain same?
Complement of a graph has nothing to do with coloring. Like we don't talk about colors when we're doing complement of a graph
So,
because you don't.
so complement of a cycle will be like nothing, like anything special about complement of a cycle.
Complement of a cycle, no, nothing special can be said. A complement of a clique is an empty graph. So clique is like the entire
Yeah.
connection, all the edges done. So that will just map into like the empty and vice versa. So like just note that if I have that, if I denote the complement of graph with g dash, then note that g dash whole dash is
G
is
again, I
equal to
guess.
g. Yeah, g. Okay, so a complement is like, what do you say? Uh, by wait, we don't go into names. Yeah, so with g dash whole dash is g. Okay, so yeah, that's a nice property to know sometimes. Okay, does this make sense so far?
Yeah, it does.
What do I want? Yeah. Okay, so these are now problems to work on. How long do you guys want? Or do you guys want to start solving and see how it goes?
One is pretty easy. Uh,
Yeah, so some people are not at all familiar with graphs. So yes, these ones are not difficult. That's,
And
I'd say fourth is mildly tricky. One, two, three, if you're like familiar with graphs before, you should get them. But if this is your first time seeing graphs, then all of these are like nice, unique ideas to think about. And like obviously, if you guys are done, you can always try out the additional questions.
for number three, can you just draw for four vertices once?
Yeah.
Yeah, name them. Okay, so you have you join V3 to V4 and V2. And
Okay.
no, V4 to V2, V2, V4 to V2.
Okay.
So this is a non-connected graph.
Yeah.
So how is its complement connected? Ah, right. Okay. You also join that edges, right?
Yeah. Oh, in fact, there's more. It's not just this edge. Oh, is the converse true? If you're done with like all four, or like you've seen them before, is the converse of three true? That is that if complement G prime is connected, does it mean that G has to be a disconnected graph? If you like speak about your ideas, or like if you have like done stuff before, just like message. I will check messages. So like feel free to share your ideas with like all of them. Especially if you're like not done with, if you're doing them for the first time. Do you guys want me to go to bonus problem in case you want to take screenshots in case you're done?
Can a graph have degree zero, maximum degree zero?
Consider the convex of a perfect cube. Maximum degrees. This is a graph with maximum. It's not going to be connected unless like it has only one vertex. But
Like this,
some
this is not. Is this a graph? Like, oh, is this the empty graph? Is
it's an empty graph. Yeah,
okay.
but it is a graph. It's not a connected graph. It's a disconnected graph.
In the third one, doesn't it come with the definition? So how to write it?
What? Third one?
It comes with the definition only that. So how to
Why
write it?
does the third one follow from the definition?
Like a normal graph plus a complement of that graph will be equal to, if we add them, so it will be equal to complete graph of
Complete graph.
the point.
Yeah. So why does that mean that a graph has to be connected?
Okay, for del G, like the maximum possible degree of the graph equals 2, does that necessarily imply it's a cycle? Or at least it's connected?
P1, P2, P3, P4, P6. Is it? Does this have a cycle?
No, it's not even connected.
No, you connected. It has maximum degree to it.
Okay, so del G equals zero, so is you said it's a empty graph. Del G
Yes.
equals del G
One.
equals one. We can say that it's just a line.
It's a sequence of lines and a bunch of random points.
Yes.
Okay, so like
Hmm.
what do you mean by
Lines by this.
yeah, it's just lines. And what
Yeah.
can you tell me exactly what do you mean by categorize for G del G equals to?
Characterize. Okay. What do you mean by characterize? So like, can you define? Okay. So can I say that every graph can be split into bunch of connected components?
No.
Yeah,
And a
it can.
single vertex count as a connected component.
What?
Does a single vertex count as a connected
Yeah,
component?
yeah. So a single vertex is a connected component. So this is one connected component. This is the second connected component. This is the third connected component.
That's
Yeah,
Okay.
it can.
Yeah. Right. So now, if I have a connected component with I vertices, I vertex connected component. Can you tell me how it looks like? So like
Which
if I have
is
a component with three vertices, must it always look like this?
no, it yeah, it like it can be a line also. Just a line with just
I mean we consider them isomorphic. This is the same as this. Like the only thing that really differentiates the two different components is just what do you say, the connections. So like if I have them v1, v2, v3, then the only thing that differentiates is if v1 is now connected to v3, that's considered different.
yeah,
but
yeah.
Okay,
So
so like
yeah,
but
that
the
these
can
two are
be
the
length
same.
the
What?
length of V1 V3 will be different if we okay.
We're not looking at them as points
No,
on like Cartesian plane.
not this. I'm talking about you said that well
Oh,
all graphs which we split into two connected graphs look the same, but I'm saying that if we have a component which has V1 and V3 connected, then it would have a different length between those two vertices than this.
okay, okay. You mean like if it was v1, v3, v2.
Maybe even V1 and V2 are connected, then it's different from the first.
So if it's like this, then it's different, right?
Yes, yes.
Good. So now, are these two the only possible conditions? We will consider v1, v3, v2 to be the same as v1, v2, v3. Okay,
yeah. These are the only possible.
these are the only two possibilities.
Yes, yes.
And uh, this is
Yeah,
when number of connected components is three, by the way. What about when number of connected components is like sorry, number of vertices in a connected component is three? What about when number of vertices in a connected component is four? Can I say that it always looks like this?
no, it can be a circle also.
It can be a cycle,
Yeah,
right?
yeah,
So can I say in general, when it's like n connected components, it's either the n cycle or it's the n line.
yeah.
Okay.
I'm getting a feeling it's true, but I can't seem to prove it right now.
Okay.
Can we just take
Again,
that for like
you can proceed
outpost?
by induction. So for the base cases
Oh,
one, two, and three, it's
that
easy
makes
to
that makes
manually check, and then you're just adding a new vertex. I can't add it to any of the midpoints of the line, like any point that's not the endpoint of a line. I can only add it to the two endpoints of the line. If I add it to both, it becomes a cycle.
sense.
If I add it to only one of them, it just
Then
becomes a
it
longer
becomes
line.
yes. Yes.
And yeah, I can't add it to a cycle since degree is already saturated for all of them. That's a connected component, so it has to be added to at least one of them. Make sense? That's how you just prove that it's only those. If G is a disconnected graph, prove that its complement is connected. Did you guys get this one?
I guess
Yes.
you can say Neptune
So
graph for this too.
how did you conclude the del G plus 2 case? Like only it's a connected graph or a connected cycle.
Yeah, so each connected component is either a so each connected component is either a line or a cycle, or
Okay,
it's
that's
like what is it, lone vertex, or it's like
what.
what is it? Yeah, just lines, circles, cycles. Like we assume that the lone vertex is a line of length with one vertex, and like this is a line with length with two vertices.
In the third
Make
question, it can
sense?
be proved by comparing the degrees of the graph. In the disconnected graph, it will be 0 plus the complemented graph. It should be greater than
So
equal
why
to.
should degree of any vertex be zero? For example, this is a disconnected graph.
Not a whole.
So like you don't necessarily have that degree of some vertex is zero in a disconnected graph.
By the way, is it true that the degree of like yeah, the complement of a connected graph is disconnected?
I don't know, you tell me. Is it necessarily true?
I think so.
It's not true. I just found a like contradictory case.
Yeah. So this is a contradictory case. V1, V2, V3. I hope you know this. Correct. So then this becomes this, this, and this. V2,
You can't go from.
no, this is connected,
Yeah, this is connected.
and this is also connected. So the converse is not true. This is a
Sure.
counterexample.
Okay, okay, makes sense.
Did you find any other counterexample, or was this the one you found as well? Three follows. Does that work? Uh, yeah, probably works. Yeah, so it's should be a valid solution. Yeah, you can prove it by induction by introducing a new vertex. So one of the most common tricks, like whenever you have to do some problem on a graph, is to do it by induction, because you can always just add a new vertex, and like one vertex usually does not mess up things too much. You might have to argue a little bit carefully, but it'll be okay.
Because we're already assuming that graph is connected. Now, if it wasn't connected at the start, then it would just be connected to one of the other vertices and then it would be connected.
Yeah, yeah. Yeah, that should work. My solution for this one is slightly different. It's
Can I
like
s- can I say that the graph completed will have n edges, and so the graph disconnected will have n minus x edges where x belong to some positive integer. So n minus x plus g complement is equal to n. So g complement is equal to x only. So and x is a positive integer, so it will be connected.
no, I don't follow. I don't. Can you repeat? So you're saying that there are capital N edges uh, in the incomplete graph.
So and the disconnected graph have n minus x edges, where x is a positive integer.
Uh-huh.
n n minus x plus g complement is equal to n, and we'll get the g complement is equal to x.
Good. And so you have g complement is equal to x, number of
And I
edges
have taken it
by
as
mistake.
positive integer, so it will be connected.
That doesn't work.
Why does
So
it become?
because what you're claiming is that if a graph has a positive number of edges, then it's a connected graph. But like this has a positive number of edges, it's not connected, right? Uh, I'm not misunderstanding, right? Like,
Can you please move to the last problem?
oh yeah, sure.
By the way, can we try this by induction? Like, for example, suppose the number of vertices be 1, then the number of vertices be 2.
If it's in, yeah, induction works. I just checked it. So like you do the base case for like v
Yeah,
equals
so
to. All you have to be careful in induction, which could cost you marks, is that you could have like all of the prior edges are connected, and then you just have this lone vertex, but that's easy to verify. Like this guy will just be connected to everything else. That'll be okay. So you have to just specify that case exclusively in your induction solution.
like for example, so one works, one edge works, obvious, one vertex works, obviously. So if we
One vertex
consider,
does not work because that's not the base case, because that's not a disconnected graph. Uh,
okay, sorry. So two vertices work, obviously.
yes, two vertices works.
So now suppose k vertices are k for this k vertices work. Like any k
Yeah,
disconnected graph and its
yeah,
complement will be connected. So if
yeah.
we introduce a new point
Uh-huh.
and we say that okay, how are we completing this induction? Here, as there will be, as this is not a disconnected graph, there will the number of edges that the number of vertices that will be connected will be less than m, less than f, k also, or less than or equal to k. But we
Okay,
just
wait. If you want, you can proceed like this. So here's how I finished our deduction, but it goes like this. So I've added this new vertex, right?
hmm,
Can it be connected to every single other vertex?
No.
No, right? So since it can't be connected to every other vertex, in the complement, it's going to have at least one neighbor, right?
yeah,
In the complement, it's going to have at least one neighbor. But I know that the rest of the complement graph is connected. Okay, so
yeah,
if I have that this is connected to one element and the rest of the graph is connected, can you show that this is connected to every other element?
yeah, obviously it works. Like you can go to one of
Nice.
the elements that's connected.
Yeah, so that is why that works. The only case that you have to be careful about is that the
If
rest
it's
of the
not,
graph is connected and we have just
that's
added this new vertex. In which case you're trivially done because this guy has an edge to everything else.
yeah.
So you're done. Okay. Do you guys want to try out the fourth one or you
Yeah,
want
yeah,
to take one second?
yeah.
If we
We have
define in the third question, if we define a set as 2 to m, where m is the maximum element, for which for which complement of g will be connected, and the statement is saying it is true, and we prove for m plus 1 such that can divide it as
So
components.
that's just the
Uh,
induction solution. That should also work.
can you give an example for number 4 when number of vertices is 3?
Number of vertices is three. Yeah, number of vertices is three, and okay, you'll have a case like this.
Yeah.
So, like for example, one, three.
Yeah, but you don't need the last two to be connected, right? It's just a connected graph.
Yeah, three. Yeah. So what it says is that if there are two distinct, oops, if there are two distinct paths which are both longest, right, then it shares a common edge. So if I didn't have this, right, there is only like this path which is, so this is the
Okay.
only longest path.
Okay. And it says that if both of the longest paths are connected, then it will have one edge in common,
At least one vertex in common.
one vertex.
Does it say one vertex or one edge? One vertex, only vertex in common. Because of like you can just think of it like this. Like for example, here there's no edge in common between longest path. Okay, that should probably one.
Okay, so the longest paths will have one vertex in common.
Yeah, so like 513 and 214 have no edge in common, but they have a vertex in common.
And for this three connected graph, what's the common vertex? And all the three are common vertex.
Like for example, if it is here, yeah, all three become common vertices. So it's at least like so
Right.
it suffices to have at least. This one, fourth one's nice. Do you guys want a hint for problem 4?
This is like by contradiction. Yes.
Do you want contradiction? Um,
Like suppose
for
not,
that,
and
yeah, suppose, you wanna go by contradiction.
like if you say suppose not, then what happens is that the longest uh the and there then two longest
Suppose
paths will have different edges. And then I guess you can show that the number of edges of the or by this the number of edges of in the original graph will be less than the number of edges in the graph formed by this. Then you will be done.
no,
What I'm
I
saying,
don't.
what I'm saying is that suppose not, then this is a connected graph. This is a connected graph. Then what I'm saying is that we can try to prove that if the number of vertices on the original graph we had was x, then the number of vertices in this graph will be x plus some positive integer. So which will be a contradiction because the number of vertices are more.
I don't see why you can show that it's x plus. What you want to show is that what you want to ideally show is that there is an even more longer path. Is what you want to show.
Uh,
That's what.
I guess so. But yeah, we can try to show this also. But what I wanted to show is that if two of the longest paths are there in the graph, and in the original graph we had x number of vertices, in this graph we will have more vertices than in the original graph.
Can you define what the original graph is?
Means original graph means the graph what
In which these were the longest paths.
yeah, in which these were the longest paths, right?
Yeah.
So this that graph will have a number of edges, but if these paths did not connect, did not have a common edge, then the
Common
number
vertex. Remember, we don't.
sorry, common vertex, then the number of vertices in this graph, which will be more than the
Why?
origin. Yeah, that's fucking fine.
I don't. like what is the new graph, what is the original graph, because you've not changed your graphs anywhere.
Okay. I guess I just have to try something. Can you show the question once? So does this question imply that there are only two longest paths in the thing?
No, not necessarily. There could be
Okay,
multiple longest paths.
but you are only
But,
choosing two.
but like but like for any two that you take, they have at least one vertex in common. Not note that common vertex is not necessarily the same for every pair. Okay, that could differ pair to pair.
Okay, can you just go to the diagram which you made? Yeah, this is a connected graph. What is the common vertex between 1, 2, 3, 4, and 7, 8, 9, 10?
In fact, they're not the longest part. Which is longest part. Like, longest part is 1, 2, 3, 5, 6, 8, 9, 10.
Okay. So this can be an
So,
idea that to show
so
that they are
that's the idea. If it's not the common part, you want to find an even longer part.
okay. That's the idea, right?
That was my proof. I like there are multitude of proofs, but the proof that I came up with had this idea.
Okay.
Yeah, then that'll be the most natural idea for this one as well. So consider how we can use the fact that it's a connected graph. Like, you know that it's connected to one, you know that's connected to four.
Yeah, what are you telling? I can't hear you because there's some noises.
Wait, let me see if I can like reduce the background. Hopefully the background noise should be a little bit better now.
Yeah.
Like as in it's not as loud. Yeah. So what was I saying? I was saying that try to use the fact that the graph is connected. So you know that there exists a path from 7 to 4, right? You know that there exists a path from 7 to 4. So what can you say about that path?
Isn't that like a longer path than both of the longest paths?
Isn't that a longer path
Like
than both of the?
1, 2, 3, 4 has length 3.
Is that
But
always true? For example, I'm just going to add a couple of vertices. I'm just going to add a couple of vertices here. Is it still the longest path? So this like 11, 12, 13, 14.
yeah, then from the part where you have those vertices, you can just take the path from there.
So the claim is that one of like this endpoint to this endpoint, this endpoint to this endpoint, this endpoint to this
Yeah,
endpoint, this endpoint to this endpoint. Out of these four paths, one of them is at least, at
longer.
least, at least one is longer. At least one is longer, which is true. This statement is true. Out of the four, at least one is longer. So you can try rigorously showing that as well homework if you want. But I'll anyways, I should have like enough questions to give a problem set. So that's the idea for question 4. So you guys can try to work out what the rigorous argument is, like why this statement is true. But the idea is that out of one of these four paths, so endpoint 1 to endpoint 1 of the other one, endpoint 1 to endpoint 2, endpoint 2 to endpoint 1, endpoint 2 to endpoint 2. One of those four is longer than the longest path in question. Does this make sense?
Yeah, but like, how can we show that? So suppose we have a length like that. So, like, is it necessary that 7 to 3 will always have length 3?
What? 7 to
3
3.
will have 7 to 3 will always have length. No, 7 to 3 will always have length 4. Is it necessary? I guess no.
I mean, not necessarily. Like, literally, path lengthwise, it's 5. And like, I can always just add a new vertex here and call it 20.
Mm,
Right? So that distance is not constant.
okay. So okay, so all other cases, suppose the word things are not connected midpoint wise, like the what the this connection does not happen in midpoint wise, then we will always have the connection where one edge will be bigger, and when we add the edges, then we will
Yeah.
always get like that works somehow.
Yeah, that works. So this will be, so one of these sides is greater than equal to L by 2 if L is maximum length. And this is also greater than equal to L by 2. With equality happening if it's midpoint, but that's fine. And I have that since they're not directly connected, this adds at least one vertex. This is greater than equal to 1. So this whole thing is greater than or equal to L
L.
plus 1, which is greater than L. Contradiction.
Okay.
That completes. Okay, so that's problems. It's 8:30. So if you guys want, you can leave. Uh, or maybe
Will
let
we?
me let me just define a tree and then we can call it a day and add the problem. So what is a tree? A tree is a connected path. Oops, connected graph with n vertices and n minus one edges. Okay, does this make sense?
No. Like, can you give an example?
Yeah, sure. That's fine. I didn't expect that to make a lot of sense the first time. Yeah, so this is a tree. So it has three vertices, one, two, three, and it has. Yeah, just give me a second.
Can we say that any graph that is connected with n edges, n vertices will have at least n minus one edges?
Yeah, you can say that.
Okay.
Can you once move to the bonus problem?
Yeah,
In the question, I made the like f of b I took as 2m and f of a I took at m, which will be congruent to m not variable. So why was it wrong?
I don't understand. Oh,
Like
wait, can we do the bonus problem after class? I want to finish trees so that like people who want to leave can leave because trees are like very important. Okay, I will like handle your doubt after that. Is that okay?
yes, sir.
Okay. Also, don't like sir. No, just say yes. Uh, yeah. Okay. Tree is a graph with n vertices and n minus one edges. Connected graph. Okay. So is this a tree?
No,
Oops.
no, no, no.
This is not a tree.
Like
Okay.
a cycle can never be a tree, I guess.
Yes. So a tree, there can't be a cycle in a tree. What did I want? I wanted does not have cycles and minus one. Can I have that there exists two paths from 1 to 3? So from 1 to 3, I have that there exists path 1, 2, 3, and I have that there exists path 1, 5, 2, 3. Can such a thing happen in a tree?
I think so.
Can something like this happen in a tree?
But I don't get you. 1, 5, 2, 3. What's the graph?
1, 5, 2, 3 means that there's a path, like there's a path 1, 5, 2, 3, and this is saying that there is the path 1, 2, 3.
No, it's
You guys see what was wrong?
1, 2, 3, 4. There are four vertices, four edges.
Yeah. But like this is not the entire graph, so there could be like 4 here, 5, 6 here, and 7 here, or all of that. And are you guys certain that this can't be a tree no matter what I do?
Yeah, because if you're adding a vertex, you're also adding an edge. And also we had established that there are more
No
number of edges.
cycles.
It has a
Wait,
cycle.
just use the no cycles in a graph fact, and then you have that 1 to 5 is a cycle.
Right.
Just use that. And can I remove any edge in a tree and still have a connected graph?
No, because a graph has at least n minus one edges.
Yes. So I will leave this screenshot here, which is important. Oops. Give me a second. That did not go as expected. Yes. I leave this screenshot here, which has like all the different ways to characterize a tree. Are you guys clear with one, two, three, four? Like how they're equivalent? So we defined it to be initially this. So this is definition, and then we show that it's the same thing as this. Okay,
Yeah, works.
and obviously connected. So be careful with that. Don't just see n minus one edges. Oh, it's a tree, and then it's not even a connected graph, and then you just end up messing up. But usually, if it's n minus one edges, it's a tree. Usually. Usually, as in like in the problem sense, where like if something is satisfied by a specific set of n minus one edges, it's probably satisfied by trees. Because trees have a lot of nice properties in general. Okay. Uh, so what? So as homework problems, you can take before like I send out the problem set at least. For homework problems, you can take what is the chromatic number of a tree, what is the least chromatic number. So this is the least number of colors you need to color a tree. Number of a tree. And then you can also work on these three problems. Oh wait, I need to define the leaf.
Is there a
Leaf.
condition for curling?
What?
You said the least chromatic number of trees, so we have some condition also.
It's given with this condition. No two vertices with the where did it go? Yeah, no two vertices of the same color are adjacent.
Okay.
Yeah. Leaf of a tree is node uh, is a vertex with vertex with
Is the answer to what is the least chromatic number of trees n minus 2?
no, it's not n minus two. For example, you can color this. Let's like get a nice tree here. I can color this with just two colors. So
Two
this
colors.
has wait. Oh wait. You said n minus two. Oops. Oops. Yeah, this tree itself I can color with two colors. I just colored this red. These two are blue, and all of these guys are red.
Wow. Okay. Okay. So like then why not two? No, not. Why not two?
Why not two? I mean, sure, maybe it is two. Who
Okay,
knows?
it's two. Is the answer two?
Yeah, answers two, answers two. Except for the trivial tree, which is this one, which is one color of it.
Okay,
For
so
this one, it's one color. For everything else, it's two.
and this construction was for every tree, I guess.
Sort of. So it's considered a breadth first search algorithm, which is something that I did want to cover, but I ran out of time. Great time management skills from me. But, anyways, I did plan like extra stuff so that I don't run out of material during class, anyways. But yeah, the idea is that you want to say what is the distance from this. You want to select an initial vertex and you want to color all vertices which have an odd distance with blue and all vertices which have an even distance with red.
Yeah.
If you take red and blue to be your two colors.
Okay, makes sense.
Okay, a leaf of a tree is a vertex with degree one. So with that definition in mind, and plural of leaf is leaves, try proving these questions. This will be like good enough homework for the
What is
one day. What?
DU? Degree.
Du is degree. Degree. This is degree of u.
Degree of what is U, right?
Yeah, degree of what is u. U belongs to capital P. Delta is maximum degree of the graph, and IB number of vertices with degree I. Yeah. Okay, are we clear on this? Take a screenshot of this. Are you guys done taking a screenshot?
Yeah.
Good. So that's it for class formally. Uh, I guess we can discuss like who is the one asking the doubt for this problem. We can discuss that now.
Oh, will you discuss this problem? So should we leave? Like, will this
I'm,
solve
I'm
this?
not going to solve this problem right now. Like take this as homework. It's a nice problem. It's not easy. This is for like people who like have good amount of experience with graphs. Like I don't think that someone who has just learned graphs is going to be able to solve it. Practice on graphs. Like I'll send a problem set. Like you can practice there.
Okay.
This is for like people who are familiar with graphs because like I know that some of the people who have joined are like strong with graphs. Yeah, you can stop recording now.